All right, let's go ahead and get started. How's everybody doing? Good? Yeah? Okay, so I hope that you saw the announcement on Piazza. There's actually still a few people that don't have accounts on Piazza. There's kind of critical information that gets communicated through Piazza. That's how you'll know when, for example, the list of research papers is up for you to take a look at and decide which one you might want to do a report on. So we've gotten about less under 30 responses so far of people that have selected the paper that they want to do. And I'm kind of surprised by the results, mostly because nobody seems to want to do my papers, but I don't know if that's because like you're too intimidated, like I'll be sitting right here like critiquing you. No, I'm just kidding. Just kidding. So a note on that though, so it looks like there's 6 students that are either graduate students or have an honors contract for this course. And there's 12 papers, and there's more than the remaining 6 slots that people have said, yes, I want to do extra credit. So not to discourage you, because the paper they chose might not be one that is available for, you know what I mean? So not making sense. So 12 papers, we're going to do all 12 of them. There has to be a presenter for each one of the 12. And we're going to evenly distribute the number of people that do a report on each of the 12 papers. So that's why we asked for your first, second, and third choice of paper. Grad students and honors contract students need to give a presentation. So those 6 or however many papers will have to be presented on, but the other ones don't have a presenter. You can get extra credit by saying, I want to do a presentation on a paper, but if your selections don't match up with available slots, then I don't know. Basically, it's a first come, first served basis kind of a thing. So yeah.
Well, can you tell us which papers, not necessarily now, but which papers are taken by the honors and grad students?
No. So what we'll do is we'll compile a list at the end of the week. So either on Friday or by Monday at the latest, we'll let you know which paper you get to do. Fair enough? You don't seem happy with it.
It doesn't solve the problem of if somebody gets a paper that also is being presented, then they themselves do not have the opportunity to present.
So first of all grad students and honors students, they have to present. So they get first pick. After them, it's kind of just wherever the chips may fall kind of thing. So you don't seem happy by my answers. So. It's extra credit. What do you want?
He really wants to present. He doesn't care about what the subject is.
Well, then pick my paper, because apparently it's unpopular. No.
How many papers are yours? Just one?
That is information you can get by yourself.
I have to click on a lot of links.
Oh, no. Okay, so just to recap that discussion, if you don't have a Piazza account, get a Piazza account, because that'll tell you the procedure for signing up for a paper, kind of an important part of your overall grade. Okay. I have an update on in-class labs. So it's been kind of a saga getting you access to FTK. We talked about FTK really briefly when we talked about different methods of acquisition. It's pretty industry standard, like the Phoenix FBI office here uses it. It's less expensive than NCASE. So NCASE and FTK are like the 2 big players when it comes to forensic software. Anyway, I've been trying to get you access to FTK since before the semester began. Turns out one of the complications that I wasn't aware of until last week is that this class was actually supposed to be held in 209. because the laptops that have FTK are like bolted to the desks in 209. So the IT guys are coming up with a workaround so that we can actually wheel a laptop cart in here. So hopefully, starting next week, we should be able to, as early as next week, maybe not next week, but as early as next week, we'll actually be able to do some in-class exercises and let you use FTK. And I think so we've been talking about things kind of a high level so far, and that'll give you a chance to really get your hands dirty, look at some actual hex values on a disk image and stuff like that. Okay, so that is in the works, and I apologize for how long it's taken, but that just was never communicated to me that this class was assumed to already be in 209 when it wasn't. So apologize for that. Okay. Another note on homework submission previously and the project. So previously I said that we would have our own custom homework submission automated grading server that if you've taken any of Dr. Dupay's courses would be pretty much the same thing. So we're actually going to switch over and use GradeScope for everything because it has an automated programming assignment grader system as well that is just going to make it easier for us. So the instructions that are currently on the course website for the process for submitting program assignments is not currently valid because we're going to do something else. Now, the reason why I'm even telling you this is because probably going to give you your first programming assignment maybe Thursday, maybe not till next Tuesday. But here's the thing. We're going to have to work out some kinks because I've never used this system before, okay? So what's going to happen is I'm going to announce the assignment, and then if there are problems, I will move the due date so that you still have a reasonable amount of time based on the problems that we run into, okay? So I'm just asking you to be patient with us as we figure out this new system and get up and running. And don't use the instructions that are currently on the website. They will change once we figure some more things out. Okay. Any questions about that? All right, let's do some review. In Little Endian, what bytes are listed first for a number? Little Endian, what bytes are listed first? Yes. The least significant byte. Yes, very good. So it's kind of backwards order, right? So when we read a number, we read the most significant digits first. Little Endian has that swapped. So, but it's at a byte at a time, not hexadecimal character at a time. So you got to remember that little detail. Very good. In UTF-16, how many bytes does it take to represent an ASCII character? Yes. Nope. Try again. Yes. Two. So ASCII, remember ASCII only used 8 bits for all characters in that character set, right? UTF-16 uses 16 bits for 2 bytes. Very good. So there's no going down lower than that, but it can also use up to 4 bytes per character for some of the other characters that are not in the ASCII character range. Okay, very good. What are some of the major internal parts of a hard drive? Yes, the head, very good. What else? Yes, the platter, very good. What else? Physical components of a hard drive.
Head arm.
Yes, the head arm, very good. Yes. Chassis, there's one more. Yes.
Actuator.
The head actuator, very good. Those are the major components. And if you can picture in your mind how they all fit together, it helps that'll help you with solidifying the geometry of a hard drive. Yeah.
What's the part?
The actuator is what actually moves the head arm and the head. So it's a little motor that makes the head go tick, 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 like that. Okay. Very good. Any other questions? All right. Did you just whisper sorry to the people on YouTube? I'm sorry. All right. What is the term for a collection of tracks arranged vertically from each other? Yes. A cylinder, very good. Why is that important to know? Well, actually, hold on. I think I have it worded better here. No, why is that important to know that that's a cylinder? Why do we have a cylinder? Describing because of the constraints, the properties of a hard disk and the head and everything. Why do we care about having these tracks, like grouping them together? More space? Not quite. Yeah. Yes, so we fill up the first cylinder first. Actually, which one do we fill up first? The innermost or the outermost? The outermost, right? Because there's more space and it's moving faster. So we use that whole cylinder first before we go to the next outermost cylinder, because we don't want that head to move very much. The less it moves, the faster we can get to the data that we're looking for. So if we can just keep writing all along those tracks as we go up, then the head can just stay in the same place if it's staying on the same cylinder. So head movement we want to minimize that as much as possible. Okay, very good. What is the smallest addressable unit on a hard drive? Yes. A sector, very good. Yeah. And how many bytes does a sector typically hold? Yeah. 512, very good. Okay. Okay, what is the CHS address of the first sector on a hard drive? Yes.
001.
001, and the equivalent LBA? Huh? 0, yes. So CHS 001 is LBA 0. Those are equivalent, okay? All right. I'm so excited, you guys. I'm gonna give you your first pop quiz. You all ready for this? Whose blood pressure just shot up? All right. It's okay, it'll be fun. All right. You laugh like you don't believe me. Why don't you believe me? Yeah, open note. What?
Is it open to other people?
No.
The sector has 512.
512 bytes into a sector. Okay, actually, can I have one of those? I forgot I need to actually explain what's going on. Okay, so hopefully this data structure looks familiar to you. We taught it as part of our lecture slides previously. So your job here is to understand the data structure, take a look at the hex values, and decode them according to the layout of the data structure. Okay? And up here you'll see I've put up an ASCII table for your reference and ease of decoding the hex values, right? Also, you'll see that it lists the decimal and hexadecimal numbers together. So if you wanted to, say, convert from hexadecimal to decimal for some reason, the values are right there. Okay? Yes?
Is this a little endian or big endian? You make the assumption.
Did I not put that on there? I thought it was, yes, little endian. Little endian. Yes. Oh, come on, you didn't do that. Oh, did I forget to tell you, you have 60 seconds and this is half of your grade. No, I'm just kidding. Yeah. Please.
Like 12 times.
The problem is that this is an image, so if I zoom any more, it won't like wrap or anything. But that's a little better, yeah? All right. Yes?
We use our computers instead of looking it up in the ASCII table.
No, this is practice, man. Okay, who can remember the part on the syllabus that talks about pop quizzes? Nobody? You all read the syllabus, right? Where does it talk about pop quizzes in the syllabus? How much of your grade comes from quizzes?
0.
0 is not there. This is just practice, okay? I want you to take this seriously because it will help. It will help you, okay? Promise. I've taken this course, I've TA'd this course, I've guest lectured in this course, now I'm teaching this course, I know this course. Take this seriously, even though it's not going to actually be computed into your grade. Take it seriously. You'll only get out of it what you put into it, okay? There's not even a place for your name. Come on. Oh, and I want the if there are any leftovers, my daughter would like them to draw on. So. Yeah. Oh, come on, you can figure that out. I will tell you this. So just like in the lecture notes, the number on the left-hand side of the hexadecimal values, that is the offset in decimal. The number on the left-hand side, that is the offset in decimal. The byte offset in decimal. Okay, who has the first value of the first record? Raise your hand. What is the street number of the first record? What did I hear? What? No. 1. Fine. This is a perfect time to make mistakes, right? You're not getting graded. And if you do it wrong, it'll make you think harder about how you're supposed to do it right. Huh?
Why is it?
Why is it 1? We'll talk about that. And here you thought all my review questions at the beginning of the lecture were pointless, right? I actually just went over this. Hey, who Who has the street name of the first record? Just kidding. You don't have to translate all the zeros, by the way. Just skip them. Who has the street number of the second record? Tricky, right? Not if you use your computer, I guess, yeah. You know what they need to do with every whiteboard, with every room, in every world around, everywhere? Raise it up a foot. Man, come on, right like that. Okay. Okay, street number of the second record. Who's got it? Who totally gave up? That's totally. I don't get it. Let's get on. Who has the street name of the second address? All right, let's do some off the cuff conversion. Right now, remember, I think I told you my brain refuses to do arithmetic. Okay, so you're gonna help me step through this so I don't make any mistakes, right? Okay. All right, let's start with the second one. This is a little harder. The first one was actually in the lecture notes. Let's just say it out loud. So what's the address of the first record? 1 Main Street, period, right? Okay, very good. And then you skip all the zeros because they're just the null blind byte. Okay, so the next record starts off 6304. Now, what's wrong with that? It's a little endian. And it's in hexadecimal, right? So really what we need to do is look at it as 0463 because 2 hexadecimal digits is 1 byte. So swap the bytes, 463. So what's 63 in decimal and hexadecimal? 63 is 99. Am I getting that right? 99, okay. That seems pretty simple. Oh wait, except we've got this 4 here, which in decimal is, can't get anything past you. Okay, so 4, now we're gonna take these, each of these hexadecimal digits, and we're gonna multiply them by a certain power of 16, right? So 3 times, let's do it this way. 3, if we were going to do the whole thing, we're just going to do number 4, but let's write out the whole thing so we get the pattern in our heads. 3 times 16 raised to what power? 0, which is 1, which is equal to 3. And then we've got 6 times 16 to the what power? 1 power, which is equal to 96. 96. Right, because that gets us the 99 that we already have. Okay. All right. So then we have 4 times 16 to the what? Other direction. 2. Other direction from 1. Sorry, a little more explicit. To the 2. So 16 squared. I don't even know what that is. What is it?
1024.
1030. Oh, this is 1024. Right? Is that what you're saying?
No, 4 times 16 squared is 1024.
Wow. All right, so we just need to add up all of these. We already know that these are 99. Right? So 99 plus 1024 is
1003.
okay, how did I come up with that number? Did I just say random? 1, 1, 2, 3.
Converted those pairs to decimal, and that is computer.
Yes, that's the mathematical way, but what really I was going for is, well, what's the street name?
1, 2, 3.
Sesame Street? One thing you heard. All right, so Sesame Street is 1, 2, 3 Sesame Street, but 1, 2, 3 is too easy because it's right, right there on the hex. So I had to put a 1 in front of it to make it harder. That's how I came up with 1.
Pretty sure.
Yes, I'm sure that that's how I did this yesterday. Yeah. Okay. Any questions about this process? Yeah.
So if it was big entities, you'd have to take each, like 4 chunks and switch the pairs. Same message?
No. So big ending and little ending does not affect strings, only numbers. So that's why it's critical in your data structure to identify that the value in the first field is a number. Because then you know, okay, well, this is a little endian system. I have to rearrange the bytes to account for little endian. Sorry, was there a question over here? Oh, okay. I just need to give you a heads up right now. The likelihood of something like this being on a midterm, all right. So, fair warning? Yes?
What are the last 2 chunks?
Give me the last 2 chunks.
So that 2042 and 72 takes that. I guess line 3.
2042, 72, success.
Space.
20 is space.
Yeah. Right? So then we're supposed to continue the message on the next line.
Yes. So,
I didn't see that next line. So I have.
All right, so- thank you. No, it's fine. So I made an assumption here, and I apologize for not explaining. So thank you for pointing it out. So this is a series of bytes where they're continuous, but we know they're continuous because we see that the offset on the left-hand side shows us the current value, the current offset at the beginning of that line. So the very first byte offset is 0, right? We haven't traveled into the message at all, into the data structure, so we're at 0. When you travel 16 bytes, you're on the next line, it continues. So this is all one continuous data stream. It just happens to be that one record takes up 32 bytes, and when you print it out 16 bytes across, it takes up 2 lines. That's just coincidence.
Okay.
Your data structure might take 48 bytes or something like that, and when you print out a hexadecimal representation of a record, it would not necessarily align with the lines.
So the byte offset just tells you how numbers your data is.
How far into the data? Yes, exactly. Any other questions? That was your question.
Can you repeat what the byte numbers are?
Yeah, so this is all just one set of data, right?
Right.
So the number on the left tells you how far into that data you are. So
Just like-
the second row is 16 bytes into the data. Second row, 32, and then 40.
It's like a picture.
Useful exercise?
Yes.
Okay, good. Then I just might do more of them.
Do one with less forgiving offsets.
With less. Gotta love the masochists, right? Okay.
Practice.
You know what? Nah, let's just keep going, right? I'm having fun. You having fun? Okay, so last time I'm going to back up just one slide because we're about to do some more math. So if you put your pencils away, I don't know, you might take them out. Maybe not. Whatever. No, take them out. So last time we left off talking about CHS addresses and how they work. So this slide is just going to be a review. We've got tracks and cylinders that start at 0. All sectors of all tracks in cylinder 0 will be filled up before using cylinder 1. Heads, they're numbered from the bottom up starting at 0. All platters are double-sided, so there's 1 head per side. And the sectors, each sector is numbered starting at 1, and they typically hold 512 bytes. So the first sector has a CHS address of 001. Talked about this last time. So logical block address. Did we not talk about logical block address last time?
We restarted.
Okay, so the problem, did I do this slide too?
No.
Yes.
Yes?
Yeah.
You were asleep, that's fine. No, just kidding. Okay, so CHS has a limitation of 8.1 gigabytes. So they came up with a different addressing scheme to overcome that limitation because they were using 3 different number slots in the data structure for a CHS address on a hard drive. And they were like, we could use these bits more efficiently if it was just one number. So let's just do that. So there's a single address instead of 3, it starts at 0. In order to convert between the two, we need to know a few things. First of all, the CHS we're going to convert from, the number of heads per cylinder, and the number of sectors per track. Does all of that make sense, or is there any confusion on that? Clear as mud? Yeah, all right, well. All right, so here is the actual formula for converting between one and the other. If you already have the CHS address, you convert to LBA if you know the cylinder head and sector, the CHS address, and then the heads per cylinder, the sectors per track, and then you minus 1 over here, okay? So, why do we have the minus 1?
Because of the 001 and 0.
Yes, CHS address 001 is LBA 0, so that we have to count for that 1 somewhere. So we subtract. Very good. All right. Cylinder times the number of heads per cylinder. Why do we need to do this? If we want to seek to cylinder 3, why do we need to know the heads per cylinder? For the logical block address, yes.
Because you write from the outside in, so you'll write the lowest, then the next one up, then the next one up. So you need to know how many tracks got up before you went in one.
Yes, exactly. So in other words, we filled up, so there's a certain number of platters. We're going to fill it each on both sides. So the number of platters times 2, that's the number of services we're covering the outermost track before we move the head in one. So we have to know the number of, if we're going to move to cylinder 2, we need to know how many tracks, not cylinders, how many tracks we filled up before we went to the next cylinder. That's why we need that information. Why do we need to know the head? Similar to what we just talked about, but a little bit different. Yes?
Same thing, just how many up you're going from there.
Yes. So We start at the bottom, right? So if we're going to head 2, we have 0, 1, and then 2. So those tracks of 0, 1, we filled up before we passed by, however, in terms of numbering with logical block address, we numbered all of those before we got to the head that we're at right now. Give a couple of blank stares, like speaking Spanish. That was really exotic. Feeling really next. Is there a confusion on that one? Yes.
Just to confirm, so when you have 2 heads for 1 platter, side is a different track, correct?
Yes.
Okay.
They're part of the same cylinder, but they're different tracks. Yes. Okay, and then the number of sectors per track. So how far into the track are you? So this is making one big assumption. This is a simplistic formula that probably wouldn't get you very far in the real world, but luckily CHS isn't actually used a whole lot on any modern drives at all. But this is making the assumption, can you see the assumption? Or do I need to tell you? What's the assumption that we're making when we multiply all of that other stuff by sectors per track?
There are sectors.
There's always going to be sectors, yeah.
Every track has the same number of sectors.
Yes, that every track has the same number of sectors. Is that clear? Right, because otherwise we would have to say, okay, well the outermost has this many, but the next one doesn't have as many, so we wouldn't be able to do a straight up multiplication if we're giving every sector a logical. Okay. All right, so with this formula, let's say that we have a disk that has 16 heads. So how many platters? How many platters? 32, 16, 8, 4, I don't know. How many platters with confidence? 8. There's 2 heads per platter. So if we have 16 heads, there's 8 platters, right? Okay. 16 heads per cylinder and 63 sectors per track. Well, yeah.
Sorry, just to clarify.
No, that's fine.
Cylinder is like a stack of platters.
Stack of tracks. Stack of tracks.
Wait. I'm gonna think about.
No, it's okay. So a track, remember, is just like a running track, right?
Yeah.
Goes around, you come back to the same spot.
Right.
Why? Because you don't want to move that head, right? So you're going to go to the next track beneath you, or actually above you, because we started at the bottom, right? The next track above you, and if you keep doing that, you form a cylinder because they're all circles, right? Yeah.
But
Do the sound effects help?
technically, you have a stack of platters.
Yes, you always have a stack of platters, but there's no word for that.
But there's multiple cylinders.
Yes, yes. So each track, so if you were just looking at one surface of one platter, each of the tracks on that surface is going to be in a different cylinder because as you go in, they represent a different cylinder. So that's what we're trying to get after in this. So the outermost, this level is representing one cylinder, another cylinder, another cylinder, another cylinder. And it's the same cylinder that this track is in this track. Sorry, I didn't explain that very well. And?
So to clarify, tracks go all the way around,
Yes,
and sectors are individual, like pieces of the track.
pieces of the track, yes. Which, yes, so letter A, the red circle, is a track. A collection of tracks vertically is a cylinder. And each little partial wedge on a track is a sector. Yes.
Two sectors of the same, two tracks in the same sector correlate with each other?
Tracks in the same sector?
Yeah, so like, we look at like C and D.
Okay, so B is the purple wedge. it's not a term that is used really that I've ever seen, but it came with the picture that I didn't want to have to redraw myself. So C is pointing to just this section right here. It's not anything else other than just that. So C is a sector.
So, but pretend B was pointing to that sector. Like, do those have any correlation? Like, since they're in the same.
Yes, so in CHS, the sector number is going to be the same in the CHS address.
But otherwise, just the address, they kind of are at the same.
So the head, if they're on the same surface of the same platter, the head address will also be the same, different cylinder.
Okay.
Okay? Good questions. Yes.
So the one platter has multiple tracks
Yes.
and multiple platters. Talking about the exact same track on each of the platters, those all form one cylinder.
Yes. Yes. So I love it. I love it when students reword what I've explained, because my wording isn't necessarily what resonates with you and clicks with you. So thank you. I love it when students reword things in your own, put things in your own words. Thank you, guys. Yes.
On that picture, you said that it assumes that there's the same amount of sectors on each
Per track.
Per track, yeah. But on this picture, like one sector is bigger than the ones that are closer. Doesn't account for the LBA transition from CHS.
The formula that I put up does not account for that.
But when you transfer it, it would just give you the address of the location of the from CHS to LBA, but not actual a size difference.
Yeah, so I'm gonna draw a picture, not on my screen because that didn't work out as well as I hoped last time. Okay, so what you're talking about is we've got a bunch of, okay, we're looking at the top, we're looking at a platter from the top, so we're just looking at one surface of one platter. So where one head would be reading. Okay, so let's say that the addressing for this platter starts right here, right? So we've got different tracks, right? Now, if we were to start at the beginning, or sorry, not the beginning, in the center, this is the shaft, by the way, so it's not actually data. If we were to divide this into 63, right, it would be pretty small, right, because we're close to the center. Now, if you were to number off 63, you might only get to here if you made them the same size as the innermost track, right? So everything from here on, would you just not use it, or do you spread them out like in this picture? I don't know. I've never made a hard drive, but do you see the issue there, right? So you don't. If it's possible to store 512 bytes of data in that small of a space, why would you use more? That's just space inefficient, right? On the outermost track where the circumference is larger. So that's what I'm saying when the formula that I had up here assumes that there's the same number of sectors per track, because we're just doing simple multiplication regardless of which track we're on. Did that clarify that point for you?
So pretty much we don't care, right?
Pretty much CHS isn't used anymore.
Yeah.
But to not know CHS would be a grave omission in your knowledge of forensics. So that's why I'm teaching it to you, not because it's in use. I gotta teach what I gotta teach, right? Okay, any other questions? That was a great discussion. Yes? So it stopped in the 90s when they started making hard drives that were 8 gigabytes. When was the last time you saw a hard drive for sale that was smaller than 8 gigabytes? Like a platter hard drive, not a flash drive. Right? So that's Yeah, that's how antiquated it is. All right, you ready to do some math? Some more math? You didn't think you were gonna have to do math for this class, huh? All right, so we've got a disc with 16 heads, 63 sectors per track, regardless of which track it is. If we have a CHS address of cylinder 2, head 3, sector 4, or 2, 3, 4, what would be the logical block address? How do we start?
2.
I'll let you work it out for yourself for a minute. So full disclosure, when I was a student, I was one of those students that when a professor would put a problem up like this and be like, okay, work it out yourself, I'd sit back and be like, well, I understand the principle, just the math work itself out. You're welcome to do that. I'm obviously not going to grade you on this, but I wish I'd been a little more participatory on exercises like this. Okay, so how do we start?
Cylinder number.
Cylinder number. So what is the cylinder number? 2. How many heads do we have per cylinder? 16. What's 2 times 16? 32. Okay, so now what head are we on? 3. So what's our logical block address so far? 35. All right, now we're going to multiply that times what? 63. Sorry, 16. Wait, what am I? Yeah, 63 sectors per track, right? Which is a number. Very good. And then we have what's our sector number on this track? 4. Yes. It's like wait, what? And then what do we subtract? 1. And the answer is
2,208.
2,208. I will take your word for it until I grade your exam. In which case, it has to be exact. Okay. Everybody see how that works? Yes.
You go over again why we minus 1.
What's the LBA? What's the CHS address of the first sector? 001, right? And what's the LBA of 001? Yes. So we put in 0 times whatever is 0 plus head is 0, CH, right? Times sectors per track, whatever it is, it's already 0, plus sector 1 on CHS. To get to 0, we have to minus 1. No big deal. It's just zeros all across. 2,208. Excellent. Okay, very good. That made you do all that math for me. Yeah, the answer is right there. Okay. Any other questions about this formula? Way better than trigonometry, am I right? Way better than trigonometry. Okay. Let's take just a really brief break. We've kind of already had a couple breaks, but let's take a break for just a second before we stop into those things. No. That's the TA. Oh, maybe. Yeah. Yeah. Sure.
It's late now.
Thank you, Bob, for subscribing to my channel. Where are you, Bob? Are you here? Bob?
I was wondering.
Thank you, Bob.
That's probably gone.
You got it?
Wait. Oh.
Yeah.
Oh, yeah. I practiced.
All right, let's go ahead and get started again so we can talk about volumes and partitions. All right. Who remembers this picture? Anybody? No? Okay, well, we talked about how we're going to think about doing drive analysis. This was kind of our model, right? We're going to start with the storage media analysis. That's going to tell us the sectors of the data. So all of that exercise about how we address sectors and everything like that, that wasn't just for fun as it was, right? It wasn't just for fun. We had to have this information of what sectors are on the disk and how to get to them in order to be able to do volume analysis, okay? And that's what we're going to talk about now. So now that we know how the sectors are laid out, we can actually discover volumes. So what is a volume? Volume is a collection of sectors. That's at the highest level, that's what it is. And that we can get to with an address. So operating system applications use it for data storage, use store file system and other structured data. So when we're doing volume analysis, we just did storage media analysis and learned all about hard disk geometry, right? The purpose of volume analysis is we're going to look at the data structures that are involved with partitioning and assemble the bytes in storage devices, okay? All right, so this is going to be just a slight tangent because it's not directly. Okay, so who's familiar with LVMs in Linux? If no one is, that's totally fine. But explaining logical volumes in Linux helps. I'm hoping will help you kind of grasp what a volume is and how it's different from a partition, because they actually are different. And knowing that difference and the subtleties between the two of them will help us speak the same language. Okay? So logical volumes in Linux, basically, let's say you're working in an operating system and you want to create. Let's stick to the slides. Okay. First of all, let's get some terms out of the way. We've got a physical volume. That's like your actual hard disk and its partitions. You have physical extents, basically just a cluster, a group of sectors. Okay, physical volume group, which is a pool of physical extents, meaning they're there. It's not just one; it's a bunch of them. Okay. And then you've got logical extents, which is just a mapping to the physical extents. Who's lost? Just kidding. This is just terminology. We'll talk it through, okay? A volume group, which is a pool of logical extents, and then logical volumes, which is concatenation of logical extents. Did I talk in circles? Yeah, so I know this is like, I do not currently plan to test you on these terms. No, I won't test you on these terms. I will test you on the concept. I may test you on the concepts of volumes. Okay, so let's use an illustration. So the dark blue rounded rectangle is a volume group. That's what we're trying to construct. So how did we get there? First, we had a physical volume, hard disk. It had some physical extents. For the purposes of this discussion, let's call them partitions. Okay? They happen to be partitions, but they could also just be like from this sector to that sector, and then from this, doesn't matter. Okay, so these are physical extents, just a group of sectors. Okay, and now we're going to say this physical volume, we want to assign it to this logical volume. So we're going to add it, and then once it's in this volume group, we can actually say, all right, I want this physical extent, and this physical extent to be one volume. So even though they're not contiguous, you see here PE1, PE2, and PEN, they're not contiguous. The file system will see them as one contiguous set of sectors, logical extents. Very meta, right? Because how do we solve problems in computer science? We had another layer of abstraction, right? So there's layers upon layers, but please don't get lost. If you get lost, let me know, all right? So this physical extent, just because it's in the group, we can actually create another logical volume that says, all right, PEN-1 and PE1 from this other physical volume that is in the group, that's going to be another volume. And we're just going to use that way. Yes?
So the squares with physical extents are basically like sectors on a hard disk?
They're not individual sectors. They're extents. So they're groups of sectors. So again, think of it like if, have you ever partitioned a hard drive?
Yeah, I didn't know what I was doing.
All right. So when you partition a hard drive, you say, all you're really saying is from this sector on the hard disk to this sector, we're going to have them be a group that we're going to call a partition. Okay. So that physical extent is that same concept, but we're not giving it the label of partition because it may not be a partition. We could just say this sector range. You see the subtle difference or not really?
But I think in general, I'm kind of following.
Okay. You think generally you're following?
Yeah.
Okay.
I can't really explain what's going on, but I just
Okay. So this is our hard disk. So let's start back here. This is our hard disk. We're going to chop it up into 4 pieces. Instead of calling this N-1 and N, we're just going to call it 3 and 4. So we've got 4 sections of the hard drive. It doesn't matter where these boundaries are on the actual logical addressable space of the hard disk, just that there's 4 divisions, okay? Now, all 4 of them, in order to make a logical volume down here, we have to add them to a volume group. That's just one of the mechanisms. You have to say, it's just, in order to give you a label, you have to be part of our club. That's all it really means, okay? So first we add it to the group here. That's what we do. That's what these dotted lines are saying. These extents, physical extents are added to the group. And then once they're part of the group, we can make multiple volumes. Doesn't even matter. We can, as long as we have enough extents, we can make as many volumes as we wanted to. And a logical volume is a grouping of extents. So this physical extent from the physical hard drive, we're just going to say, all right, you are going to be part of this logical volume now. So what that really means, so here, PE1, PE2, you're reading along. If you were to just traverse the whole logical volume, you would read. Then you get to here, you keep going. Read, because it's part of the same logical volume. Then we get to this boundary right here. This is not part of that logical volume. So from the volume's perspective, the next sector in that volume is right here. Read. Okay. So the logical addressing of extents in this group, this logical volume, goes from here to there and then continues on there. That helps? Is there anyone that's still confused?
I have a question.
Yes.
How do you know which physical extent goes to which logical volume? Like you have PE1, PE2 on root. How do you know it's not going to go to like hollow or something?
Because PE3 is part of cone.
So you just know.
So you, okay, so if you're gonna make a logical volume, you get to do whatever you want. Yeah.
Oh,
Yeah, that's the beauty of logical volumes, is that you can say, I want, essentially you can do your own kind of striping, right? So you can say, I want to take this partition from this hard drive, this partition from this hard drive, this partition. And they're logically, from the system's perspective, they're all going to be one volume, even though they're on completely different disks. Okay? You can even see over here, this physical volume, it's a separate volume, they're separate disks, but yet home actually spans the physical extents from either one. Okay, so partitions have to be on the same disk. Volumes don't. That's one of the main differences between volumes and partitions, and I hope that you can see why you would want to do that. Because, okay, so I maintained the servers here for the SETCOM lab for years, and we had a bunch of servers that we would have multiple hard drives, but I didn't want the operating system to see multiple hard drives. So what I would do is I would make a logical volume that spanned all of them to basically make it one logical disk. One disk to the operating system. The operating system, all I tell it is, hey, all you need to know about is this logical volume. That's where you're installed. And so it would see the address space of all 4 hard drives installed in that server, even though really it was broken up, right? It didn't know. All it knew was, I have this address space. Okay, I could have done it in some funky order. I use this one and this one and this one. I could have done whatever I wanted to. The system wouldn't have known. It's a logical grouping of extents. Okay? Yes?
So logical volume is a concatenation of logical extents. Does it matter which way you can get?
No.
So it's whatever address space in there. You just concatenate the addresses of the logical extents.
Yes. Yeah. So the logical volume is going to have a different address space than the extents that make up that volume, right? And if we were really, for some reason, we could even do these in reverse order, right? So if we're traversing through root, we would start here, get to the end, and then come back here, and then read to the end. We could do that. And from the volume's perspective, that would be one continuous series of addresses. It wouldn't know. Yes? Yep. Is anyone at all confused? If you're not comfortable saying that you're confused, I do have office hours today after class. So I don't want anybody to be confused about this because it's kind of extra material, but it's kind of cool to know about. And if you understand logical volumes, it can be a real benefit to you. Okay, yeah.
In this, where would a logical extent be?
Okay, so the logical extent is really just a mapping here. So once it's part of the logical volume, each of these is kind of a logical extent, but the concept of a logical extent isn't as important in this construct. I don't know if I directly answered your question or not, but basically don't worry about it too much because I don't really know. No, it's not too important. Okay, so partitions. Maybe I should have done this topic first before I went into volumes, but partitions is a collection of consecutive sectors in a volume. So things just got really extra crazy because you can actually partition a logical volume. So you could do this, take a hard drive, partition it, use those partitions to create a logical volume, one volume, then you can partition it again, right? You can do that. And actually, there's use cases where it makes sense to do that. But that's neither here nor there. So sectors in a volume. This isn't necessarily a logical volume, okay? Volume here could mean a disk, partition, or a logical volume. And that's why I introduced logical volumes to you, is because a volume can be many different things, but a partition is just consecutive sectors. Okay. All right. Each OS and hardware platform uses a different partitioning method. All right. So this is a partitioning example. Let's say we have this hard disk where the green area is addressable space. Okay. So we can chop this up into 3 different partitions and say, all right, this is going to be C volume, that's going to be D volume, that's going to be E volume. And these appear separate to the operating system. The operating system, if it doesn't peek at the actual hard disk information, it sees those as separate disks. And so that's, yeah. Any question about partitions? Okay. What is the purpose of partitions? It helps to organize the layout of a volume. It's the essential data through a volume, obviously, are the starting and ending location of the partition. Now, and it's also common for partition systems to have one or more tables, and each table describes a partition. So you have the starting sector, ending sector, the type of partition. Okay. Any question about this information? Yeah.
What does it mean by type?
We're going to get to that in just a second. Okay. Master boot record. This is a big one. There are a few things that you should not leave this class having not learned. This is one of them. Okay. Master boot records are the first sector on a hard disk. Always the first sector. Why? Because then you know where it is. All right. So previously, when we analyzed the hard disk to figure out where all of its sectors are and how to address them, that gave us an understanding of how much space we have. This tells you how it's organized, okay? So that's why it's so critical that it be the very first sector. Now, there's a few different pieces of information that are part of the master boot record. The first is the executable code that actually boots the computer, but you only got 446 bytes. So a lot of times what happens is those 446 bytes just kind of tell the boot loader where to get the rest of the information to boot the computer, okay? So that's not what we care about right now, though, because we're doing volume analysis, right? That's where we're focusing our attention right now. Just happens to be that there are 4 partition entries in the master boot record. Now, these so these are considered primary partitions. There are other terms like extended partitions and other things like that. We're not going to get into that, but I just want those that are familiar with partitioning to know I'm not leaving it out. We're just going to focus on. All right, so each of these partition entries has the structure that's shown on the next slide. Okay, so each one of these has a data structure that is well-defined, and we're going to talk about that. And you have 4 of them. So what's on the next slide, there's 4 of those in the MBR. Okay, boom, there it is. All right. Let's talk through it. So the first byte is indicates the state of the partition, 00 for inactive and 80 for active. Why they needed a whole 8 bits to represent 2 states, I don't know, and why they used one that wasn't at the beginning, I don't know. But that's how it is. So it's active X80. All right, now the next couple of bytes are the CHS address. For any modern platter hard disk, those are going to be zeroed out. Okay, so usually you won't have anything there. Type of partition, we're going to talk about that in just a second. And then the end CHS address. And then here we have the logical block address for the start and then how long it is. So what's the main difference that you see here between how CHS does things and how LBA does things? What two pieces of information does CHS give you? The beginning and the end. What two pieces of information does LBA give you? The trick question, I promise. What? How long it is. Tells you the first sector in with its logical block address, and then not the ending sector, but how long it is. So how would you get the ending sector? You had them, right? It's not a trick question, but yeah. Yes, what's up?
If this is always the first sector, isn't the number of sectors between this and the first sector in the partition the same, just the LBA of the partition?
I'm sorry, I didn't quite understand.
So here on 08, we have numbers of sectors between the NBR and the first sector.
Yes.
Isn't that the same as just the address of the first sector, the LBA? If NBR
Yes.
is LBA 0?
Yes. 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 Very good. And then there's 4 of these. Okay. So you'll have one for each of the 4 partitions that the MBR can store. Okay. Any questions about this? Okay. So here's some additional things that you need to know. First of all, there's the maximum addressable storage space is 2 terabytes. Terabytes? I hate trying to pronounce those. Okay, 2 terabytes, 2 to the 40 bytes. So this is in the process of being superseded by the GUID partition table or the GPT scheme. So basically they said, dude, we're making hard drives that are bigger than 2 terabytes. We met yet another limitation of an addressing scheme. We went from CHS to LBA, that has a size limitation, so let's bump it up and come up with a completely new scheme, because if you look back here, there's not a lot of extra space to put partition information, right? So the GPT, sorry, click too many times. The GPT scheme is way more flexible, has way more information about each of the partitions in a volume. Allows for a lot bigger drives. A little bit more complicated, but we're not going to explain it here. GPTs offer limited backwards compatibility. So basically, instead of the first partition entry in the MBR, you have what's called like a protective entry that says, whoa, hey, yes, there's stuff here, but so don't just assume that the hard disk is empty, because it's actually, if you want the partition information, you have to go somewhere else. That's basically what it says. Because if you had nothing, then something reading the MBR would be like, what? There's nothing here. Okay, I'll just write over everything. So got to have something protecting that in order to do backwards compatibility. Okay, so if you want more information, Wikipedia has actually surprisingly very good technical information on the master boot record, the GPT, and then there's tons of supported partition types. So getting to your question, go here. And there's so many partition types. And the fun thing is, the number that identifies a partition type is not a one-to-one matching. So yeah. Okay, that's a good place to stop for today. We'll see you next time.